Okay, so differentiability, the last little exercise of this topic. Now, for a point to be to have differentiability at a point, or for a point to be differentiable, we call it differential, like a function is differential, or smooth at x is equal to a if it satisfies two conditions at that point. And that is that the function is continuous at the point x is equal to a, or the graph passes through the point where x is equal to a without any sharp corner, and the resulting tangent is not vertical there. Okay, so essentially we're going to be trying to avoid gaps, and we're going to be trying to avoid functions like the absolute value function. Y is the absolute value of x, which looks like this. Okay, so there's a sharp corner just there, means it's not differentiable at that point. Okay, so let's jump in and have a look at an example of this. Okay, it's pretty simple, and we will work it out from there. So we've got two little examples here. So test each function for continuity and then differentiability at x is equal to 0. Then sketch the curve and write down its domain and range. Okay, so to test a function for differentiability at a join between pieces at x is equal to a. So in this case, we're looking at 0 and 0 again in this case. So we're going to test the function is continuous there, and if it is, we're going to look at the derivative on the left and right to see whether the join is smooth. So basically, it's not going to make a big jump type thing. All right, let's start with A. So testing the point 0. So 0 squared plus 1 and 0 squared minus 1. Well, in this situation, we don't actually have that continuity at point. So therefore, no continuity, not continuous at x is equal to 0. Okay, so it's not continuous at x is equal to 0. Okay, so it's not differentiable there. Okay, so let's so then we're going to sketch and write down the domain and the range. So sketch. Okay, here's a little picture here. So it's x squared plus 1 when x is less than or equal to 0. So at plus 1, okay, and it's including this value here. Okay, and it's a function of a parabola that goes up like that. Then it's x squared minus 1 for x is greater than 0. So and it's going to go this way here. So it's the two different halves there. Okay, so therefore the domain is all real x. Okay, so domain's fine. But the range is when, so in this case, it's going to be from negative infinity up to, and not including the negative 1, okay? And then we are going to include the 1, and then it's going to go on to infinity up that way. Okay, so basically we've got this gap in the middle where the range doesn't exist. Okay? So in other words, the range is all real y except between negative 1 and 1, not including the negative. Okay, that's part A. Let's have a look at part B. Now part B says we've got x minus x squared for x less than or equal to 0, and then we've got x for x is greater than 0. Okay, so at x is equal to 0, we've got x squared minus x, and we've got x. So it's 0 minus 0, which is equal to 0, and it's just 0. So therefore it's continuous, and if it's continuous, then we need to check for differentiability. So to check for differentiability, so part 1 is to check if it's continuous, which case it is, and then now we need to look on the left and the right to see whether the join is smooth or not. Okay, so to do so, we could do a table of values, or we could just draw the picture. Let's just draw this picture. We'll just draw the picture, and we'll see if it's the case. Okay. So here's the function here. We've got x squared minus x for the first bit. Okay. Actually, you know what? Let's make it easy. So when x is greater than 0, we've got just the function y is equal to x. Okay, so it's an open circle here, and it's like that. Well, it's probably actually a bit more shallow than that because it should be at 45 degrees. Okay, so that's y is equal to x along there. And for the other bit, we've got x squared minus x. Okay, so x squared minus x. Let's do a quick little table of values for that one. Okay, so we've got x and we've got x squared minus x, and that's 0, -1, -2. So x squared minus x is equal to 0. Okay, -1 squared is 1, minus 1 is equal to 0, and -2, which is 4, 4 minus is equal to 6 in that one there. I'll tell a lie, it should be 1 minus plus 1, so that one should be 2 there, not 0. Okay, so 0, 2, and 6. Okay. So -1 squared, and then there's 1, then plus the 1 is 2. Yeah. Okay, so 2, and then this side's so it's gonna be shooting up like that. Okay. So it kind of looks a bit like that. Is that smooth? Not 100% sure. Let's double check this one on Desmos, because we love our good old Desmos. Okay. So we've got y is equal to x squared minus x, and that's when x is less than or equal to 0. Okay, like that. So it looks like that. And then we've got y is equal to x when x is greater than 0. So if you have a look at this, no, not really. It sort of comes down and then shoots back up again. Okay, kind of like we see here. So it's not quite as nice. It's more of a straight up like that. So in this case, it's not really differentiable there, because it's not quite, it makes a bit of a sharp turn there. If it was more smooth, then it would be differentiable, but in this case, not really, because it does make that sharp sort of turn up like that. Okay, so both the examples were pretty much a no. Okay, so let's have a look and, change this around a little bit. If this was plus, have a look at this one instead. This one's much nicer. It actually comes down, and then it keeps actually following that trend, and then it comes back up like that. So that one would be differentiable, but with the minus there, it's not the case. If we change this to minus x though, this one, this is definitely much better on this side. So this one would be differentiable because this one just keeps following that. You can see it keeps following that nice, smooth, straight down like that. Okay. So there's two other bits that we need to talk about differentiability. Okay, first one's vertical tangents. So a vertical tangent is basically like saying if you have a tangent that is essentially a vertical line. So if we have a look at, for example, f of x is equal to x to the third. Okay, so something like this. Okay, let's have a quick look on Desmos again. So f of x equals x to the third. Okay, and this is a really cool looking function like this. It's basically just an x to the power 3, but it's on its side. And you can see that we have a tangent, a vertical tangent, when x is equal to 0, to go straight up and down like that. Okay, so because that vertical tangent, well, if we were to find the derivative of this function, so that's f of x is equal to a third comes out the front, and it's x to the power of -2 on 3, like that. And as you can see, the function of our derivative is actually got an asymptote here at that tangent there. So if we keep going up, it's going to get closer and closer, but never touch. And now the reason why that 0 doesn't exist, so if we have a look back over here, the derivative in this case is a third x to the -2 on 3. If I turn this back into with positive indices and stuff, so this is the same as 1/3 times x to the -2 on 3, which is the same as 1/3 times 1 over x to the 2 on 3, which is the same as 1/3 times 1 over the cube root of x squared. So if I put that together, this would be 1 over 3 lots of the cube root of x squared. Now, if x was equal to 0 in this case, so if I substitute 0 into there, I get 1 over 0, and that function can't actually exist. So that's how we get that vertical tangent. In that case, our function is going to be undefined, our derivative is going to be undefined at that point there. So that's for a vertical tangent. So that's the vertical. Now let's look at another type of problem. I guess we could call it, in the cusp. Okay, so let's have a look at the function. So it's another function with a fraction. So it's x is equal to fx equal to 3. So f dash of x is equal to 2/3 x to the negative a third. So again, putting this one out, 2/3 times x to the negative a third, which is equal to 2/3 times 1 over x to the third, which is equal to 2 over 3 times 1 over the cube root of x. Putting it together, we get 2 over 3 lots of the cube root of x. And again, x cannot be equal to 0 in this case. So we're going to have another issue here too. And in this situation, it's not going to look as nice as this one here. Okay, so if I put in my function x is equal to the negative negative should be 2/3, not 1/3. I don't know why I was putting 2's there. Or 1's there, I should say. So that should be x squared there. So negative, to the positive 2/3. We get this cusp. Oh wait, no, that's the derivative. Never mind. That bit was fine. So yeah, f of x is equal to 2/3. So what you can see is at y is equal to 0 again. Sorry, x is equal to 0. We've got this, this point here where our line comes down and it shoots back straight up in the opposite direction like that. And this makes what we call a cusp. And we can't find a tangent. We can't draw a tangent there. And so the derivative doesn't exist. With that being said, that's the end of that video. And that's the end of our first look at our differentiation topic. After this, we're going to be looking at polynomials, if you are following the extension line, but then we'll come back and look at some more calculus in a bit. With that being said, that's the end of differentiation for now, and we'll have a look at some more stuff in the next topic.